This video summarizes our work on bootstrapping multilingual semantic parsers using large language models. I am Abhijit Avasthi, and this is joint work with Nitish Gupta, Vidisha Samanta, Shachi Dave, Sunita Saravgi, and Partha Talukdar during my internship at Google Research India. Semantic parsing is the task of mapping natural language text to logical forms. It has several applications ranging from question answering over knowledge bases, which require converting questions in a natural language, to executable SPARQL queries. Another application is converting user instructions to API calls in virtual assistants. For example, mapping a user query to set the alarm for 8 a.m. to its logical form containing intents and slots. Similarly, semantic parsing is required in programming assistants to map text descriptions into executable code. This work focuses on task-oriented semantic parsing, which requires converting natural language utterances into logical forms with intents and slots. Intents specify high-level goal of the utterance, for example, creating an alarm, and slots specify the final level details, for example, the date time of the alarm, where slot arguments are strings grounded in the input utterance. Our goal is to scale semantic parsing models across multiple languages. However, annotating semantic parsing datasets at scale is costly, as it requires human experts who can specify logical forms in a formal language. One of the most common ways of bootstrapping semantic parsing datasets across multiple languages is to translate English datasets using off-the-shelf machine translation services. So, as a first step, utterances from the English dataset are translated into a target language, for example, Hindi, using a machine translation service. In the second step, the slot values in the English logical form are replaced with tokens in the target language copied from the translated utterance. In this particular example, we see that 8 a.m. gets replaced by Subah 8 baje, which is the translation of 8 a.m. in Hindi. This work explores how well large language models can help us translate semantic parsing datasets across 50 typologically diverse languages. There are two potential advantages of using large language models over off-the-shelf machine translation services. The first advantage is large language models are typically trained in a self-supervised manner while only requiring a few human-labeled examples for learning a new task. On the other hand, machine translation services often rely on large human-annotated datasets, particularly for low-resource languages. The second advantage is large language models can be easily customized via few-shot prompting to generate in-domain translations, while machine translation services can often be brittle for out-of-domain instances. Let us now look into how we translate an English dataset into a target language using a large language model. With the help of human translators, we first collect translations of a small seed set of English examples in the target language. We choose at least 20 seed examples per domain to cover each intent and slot at least once. Using the seed example translations, we prompt the large language model to translate all the English examples into the target language. To improve the quality of the translated data, we generate multiple diverse translations using temperature sampling techniques and filter out the inconsistent samples as we describe in the next slides. Given a test example in English, we dynamically construct a prompt containing few short translation examples sharing the same intent or slot from the seed set. The prompt concatenated with the test English example is fed as an input to the large language model to generate the translated example in the output. To mimic how users can frame the same instruction in a variety of different ways, we generate multiple diverse translations for a given English example using temperature sampling techniques like nucleus sampling or top case sampling. Although sampling-based decoding methods can provide us with diverse outputs, they are known to generate noisy and inconsistent text. To filter out the inconsistent samples, we make use of a simple string match-based technique. We discard the samples where slot values in the logical form do not appear exactly in the translated utterance. The samples shown on the right have slot values highlighted in red that do not appear in the translated utterances. Such examples are discarded. For samples on the left, the slot values appear exactly in the translated utterance, and hence such examples are retained. We conduct our experiments on two public datasets, MTOP and MASSIVE. MTOP contains examples from 5 languages, while MASSIVE contains examples from 50 typologically diverse languages in addition to English. For both MTOP and MASSIVE, we translate the English training dataset across all other languages. We work with PaLM as a choice of our large language model and experiment with 8 billion, 62 billion, and 540 billion sized variants of the PaLM model. For the datasets translated using a machine translation service, we borrow the examples generated by the translate and fill method, also referred as TAF. Finally, we fine-tune an MT5 large model on datasets from all the languages to obtain a multilingual semantic parsing model. Let us now look at how effective are the datasets translated by a large language model compared to those translated using an off-the-shelf translation service. In this figure, we present our results on the MTOP dataset. We compare the performance of MT5 models fine-tuned on datasets translated by 540 billion and 62 billion size PaLM with the datasets generated by the TAF baseline that uses an off-the-shelf translation service for translating datasets. We also compare with fine-tuning MT5 on the few short seed examples used for prompting the PaLM model. We compare our models on 5 different languages: German, Spanish, French, Hindi, and Thai. On 4 out of 5 languages, fine-tuning on datasets translated by the 540 billion PaLM outperforms the TAF baseline. We observe higher gains of more than 5 accuracy points for low-resource languages like Hindi and Thai. We also observe that datasets translated using the 540 billion PaLM model are consistently more effective in comparison to translation using the 62 billion PaLM model. In this figure, we compare with fine-tuning on datasets that are fully translated with the help of human annotators. We refer to the human-generated translations as gold translations. We observe that fine-tuning on datasets translated using the 540 billion PaLM model achieves 93% of the gold performance with 30 times lesser human supervision. However, across all the languages, we also notice a considerable gap with respect to fine-tuning on the gold translations. We expect this gap to reduce with future improvements in large language models and text decoding algorithms. Next, we scale up our experiments from 5 languages to 50 typologically diverse languages in the MASSIVE dataset. In this figure, we plot the difference between the accuracy obtained by our method using the PaLM 540 billion model and the TAF baseline that relies on off-the-shelf translation services. We observe that our method outperforms TAF baseline on 41 out of 50 languages, and for 9 of these languages, we observe larger gains of more than 5 accuracy points. Finally, we investigate the impact of decoding strategies and data filtering on the downstream accuracy of the fine-tuned parsers. We observe that our method of filtering slot inconsistent examples provides gains independent of the decoding strategy. Compared to greedy decoding, we observe that generating translations via sampling techniques followed by filtering provides better results, and further sampling multiple translations provides us additional gains. To conclude, the key takeaways from this work are that large language models can be more effective than translation services for translating datasets across multiple languages. In our experiments, we observed gains in 41 out of 50 languages over a strong translation service-based baseline. We also noticed that sampling multiple translations, decoding strategies, data filtering, and the size of large language models have a significant impact on the downstream effectiveness of the translated datasets. Thank you.